First, we would like to thank the conveners of this symposium for nominating this presentation as a keynote talk. Plate tectonics explains very well the distribution of volcanism on the modern Earth surface and also through the Phanerozoic and probably most of the Proterozoic. However, for the Archean, it's a less convincing tectonic paradigm or model, largely because some of the key geological tectonic elements that are actually evidence for the existence of plate tectonics are absent from the Archean geological rock record. This includes ophiolite slices with the important sheeted dikes, high-pressure blue schist metamorphic belts, accretionary prism tectonic zones. So that then raises two questions. What were the drivers for Archean magmatism, and what were the geodynamic settings? To address these questions, we will use the geological evolution of the late Archean Kalgoorlie Terrane in the eastern Yilgarn Craton, Western Australia, as a case study. In this slide on the left-hand side, there's a simple map of the Yilgarn Craton showing in pink the distribution of the widespread granitoid plutons, including TTG sweet rocks. In green, color-coded for different ages, are the associated volcanic and sedimentary greenstone belts. We're going to focus very much on the history of the Kalgoorlie Terrane here in the eastern Yilgarn Craton. And on the right is a geological map of the southern Kalgoorlie and Konalpi terranes from a paper by Jones et al. In 2020. The major stratigraphic subdivisions are color-coded green and purple for the oldest Komatiite basalt association, overlain by the straw yellow felsic and volcaniclastic association, and overlain in brown by the late basin sedimentary association. Now that stratigraphic architecture is represented in another diagram here from Jones et al., which shows the stratigraphic column or history of this succession. Initially, the oldest Kambalda Sequence association of basalts and Komatiites ranges in age from 2720 to about 2690 million years. It's overlain by the very felsic Kalgoorlie sequence, typified regionally by the black flag group, beds or formation, which ranges in age from about 2690 to about 2665 million years. And that's then succeeded by the younger late basin succession consisting of two subdivisions, the older Marugal formation and the younger Currawang formation and correlatives. And the age range of the late basin sequences is from at least 2665 to less than 2658 million years. In the middle, we show the timing here of the emplacement of the major granitoid pluton suites, including the TTG high calcium mafic granitoids, which were emplaced during Kalgoorlie sequence and late basin time, the low calcium or more potassic granitoids, which were emplaced during late basin and beyond time, as well as were the late cyanites, which are important to gold mineralization. On the right, we see the depiction of the principal deformational events, an early basin-forming extensional event that spans most of the history of the Kalgoorlie Terrane, followed by a D1 deformational event, which Jones et al. Relate to the emplacement of upwards rising diaperic plutons into supercrustal greenstone stratigraphic sequences. And these were followed by a succession of compressional events, D2, D3, D4, which began just before the deposition of the Currawang sequence late basin system. To trace the geological evolution of the Kalgoorlie Terrane, we're going to look at the principal lithofacies which are preserved in these three major stratigraphic associations, beginning with the Kambalda sequence, in which the ambient sediments are hemipelagic black to grey mudstones and cherty sediments, which clearly indicate an open ocean, deep and quiet water setting well away from any significant landmass. The basalts beneath the Komatiites are tholeiitic, and those above are high magnesium basalts, and the basalt belt extends for greater than 600 kilometres along strike. There are cogenetic dolerites. The lavas range from pillow to massive sheets with variable development of hyaloclastite breccias. There are no pyroclastic deposits, and this then reinforces the interpretation of the eruption environment as a submarine, very deep water setting where water depth and hydrostatic pressure suppressed explosive interaction between the erupting lavas and the oceanic water mass. The Komatiites are also represented by lavas and subvolcanic intrusions. The lavas typified by spinifex orthocumulate textural zonations. They're 1 metre to several tens of metres in thickness, and there are localised development of haloclastite breccias. The subvolcanic intrusions are typified by olivine, adcumulate, orthocumulate, dunite sills, which can be up to hundreds of metres in thickness, and the Komatiitic Association also extends for more than 600 kilometres along strike. So the depositional setting can be represented by this three-dimensional block cartoon diagram, which shows cogenetic seafloor lava flow fields and subvolcanic intrusive sills. And this model applies to both the Komatiites and to the basalts. So the volcanological setting was a submarine, large igneous province, driven by a very active mantle plume event, the evidence for which is the high temperature Komatiites, as well as the abundant high magnesium basalts. So if you like, imagine a young flood basalt province such as the Columbia River basalts that has been erupted underneath water, and you have it for the Kambalda sequence setting. During Kalgoorlie sequence time, there were major changes, and these include an increase in felsic volcanic activity, represented mostly by large volumes of dacites, minor andesites, and rhyolites. Some of the dacites have chemical affinities to contemporaneous TTG granitoid plutons, which were erupted extensively during this particular time. There are also voluminous felsic volcaniclastics, including some derived from significant explosive eruptions. There are no Komatiites. There are still some basalts and associated dolerites, which testify to the ongoing influence of the mantle heat engine for the felsic magmatism during this particular time interval. The ambient sediments are still black to grey dark mudstones, indicating the ongoing existence of a deep water, quiet environment. These are, however, associated with coarse volcanic conglomerates and sandstone turbidite clastics. Importantly, these clastics lack basement-derived debris, and by that I mean deeper-crustal metamorphic, metasedimentary, and metaplutonic clasts. And that indicates that these were not derived by the erosion of uplifted orogenic tectonic belts. So the provenance for these clastics is mostly local volcanic. There are different compositional associations, from purely felsic to mixed felsic to granitoid to purely mafic to mixed mafic and komatiitic. Very importantly, the mafic and the ultramafic class have been geochemically fingerprinted to be compositionally identical to the underlying basalts and komatiites in the stratigraphic associations where they occur. That means that the older Kambalda sequence must have been at least locally uplifted and subject to erosion at this time. In addition, the granitoid class appear to be related to the TTG regional plutonic bodies. And this indicates that at least some of these diapyrically rising plutons became emergent and then subject to erosion. Now, conglomerates require high energy shoreline or subaerial reworking environments and then resedimentation. So in this open ocean environment, there were therefore also dispersed volcanic islands. Here's an image of some of these mixed class conglomerates, granitic felsic, mafic ultramafic, mostly felsic, and mafic. And the interpretation of these sequences is that the older Kambalda sequence of Komatiites and basalts were diapyrically intruded by uprising granitoid plutons, some of which caused volcanoes that became emergent and shed their debris into the associated basin. Some of these diapyric plutons then continued to rise and then caused uparching and emergence of the Komatiites and the basalts, which then began to shed detritus into the associated basin, and then eventually the plutons themselves became emergent and shed detritus. So in the associated black flag group type lithofacies, we find a provenance sequence that reflects a progressive unroofing of deeper levels of the stratigraphy. An important volcanological facies in this time interval are monomictic megaturbidite felsic tufaceous sandstones. Now these occur throughout the belt, Jundee right down to Kambalda. They represent large explosive felsic eruptions that produced pyroclastic flows which entered the ocean, mixed with seawater, and transformed into very large submarine turbidity currents. They also reflect more volatile rich magmas, shallowing of the volcanic centers either through eruption and constructional growth and or through uplift. And an obvious mechanism for that uplift is the jacking up by these diapyrically rising subvolcanic plutons. So the paleogeography was still of an open ocean deep water basin, punctuated by localized volcanic islands represented perhaps by stratovolcanoes, and also rising and emerging dacite lava domes jacked up by the intrusion of subvolcanic diapyric plutons. When we get to stage 3 or late basins time, there are also significant changes. And the deposits of these late basin sequences are dominated by coarse, cross-bedded, channelized conglomerates and sandstones. And very importantly, this represents the first level in the stratigraphy where we see large-scale planar and trough cross-bedding and scour and fill structures, which are indicative of high-energy tractional environments. The older late basin sequences, represented by the Marugal beds, are still largely monomictic, tufaceous, felsic volcaniclastic, although there are some granite plutons there. And they reflect ongoing explosive volcanic activity during Marugal beds time. The younger or later late basin sequences, such as the Currawangs, are much more polymictic and include far-field derived BIF fragments, metasedimentary and metaplutonic clasts, and therefore are very different to the Marugal succession. So by this time, the paleoenvironments had become high-energy traction environments represented by alluvial fans, fluvial braid plains, and subaqueous fan deltas. And these reflect then the emergence of the Kalgoorlie Terrane from a submarine setting to a subaerial setting, representing a regional uplift and regression of the ocean. So what caused this uplift? And that then gets us into considering the geodynamic regimes that may have been influential during the history of the Kalgoorlie Terrane. To address this, we will consider the various geodynamic or tectonic models that have been proposed for the Archean throughout its history, beginning with the early Hadean, when the Earth was considered to be a molten mass. There was a magma ocean which progressively cooled to form a plastic protocrust. We find no evidence of that older history preserved in the Kalgoorlie Terrane, so we'll put a big red cross through that option. However, a very important model is that of a continuous stagnant lid or crustal or lithospheric shell. That is, instead of there being discrete lithospheric plates, there was a single shell, crustal or lithospheric shell, encircling the Earth. And the evidence of that lies in the absence of clearly defined lithospheric plates, subduction zones, and spreading ridge systems. That outer shell was probably very mafic to ultramafic in composition, up to about 30 kilometers in thickness, produced by intra-lid volcanism, producing large igneous provinces and igneous plateaus. And it was so dense that it was not isostatically buoyant. Hence, there were very few continental land masses until late in the Archean, when the production of felsic granitoid plutons then made the upper crust much less dense and buoyant, and led to the emergence of land masses. We've already given a great big green tick to the importance of mantle plume dynamics in the Kalgoorlie terrane, represented by the Kambalda sequence, Komatiites and Basalts, but also reflected in the ongoing heat effect that produced the felsic magmatism in the Kalgoorlie sequence, represented by the granitoids and the volcanics. And in addition, during this time, there was probably a process of crustal dripping or delamination going on to explain the genesis of some of the TTG plutonic bodies. The low and medium pressure TTGs can be accounted for by partial melting of the lower to middle mafic crust, but the high pressure TTGs require the delamination and detachment of slabs of the lowermost crust and the sinking or dripping of those into the uppermost mantle, where they partially melted and produced buoyant felsic high pressure TTG plutons. We've already also given a green tick to granitoid diapism, which involves the buoyant diapiric uprise of these granitoid plutons, causing uparching and doming of the supercrustal sequences and the simultaneous downwarping or sagging or sagduction of those supercrustal sequences adjacent. And the structural effects have also been studied by Jones et al., which showed that around some of these plutons in the Kalgoorlie terrane, there are plunging structural lineations along the margins of the plutons. There are concentric and or circumferential foliations, and there are also concentric and circumferential extensional shear zones, which accommodated the uprising of the diapirs into the supercrustal greenstone sequence, which was simultaneously subsiding. Nonetheless, we also have to explain the deformational fabric that's preserved not only in the Kalgoorlie terrane, but other terranes of the Yilgarn Craton. And this is reflected by northwest tectonic trends, east-west shortening, and the crustal duplex structural profile that's been imaged throughout much of the Yilgarn. This can only be explained by a significant crustal compressional event. And in the absence of Phanerozoic style subduction, those criteria that we've already discussed, the preferred model is mobile lid and localized subcretion. Now, this is represented in this diagram from a paper by Jean Bédard, depicting what happens, what he thinks happened in some of the Canadian cratons, where progressively the developing continental nuclei were enlarged by the lateral accretion of underthrust slices of Archean oceanic crust, that's very different to modern oceanic crust, and the lack of evidence of deep subduction, which is important for modern day subduction. So this then also brings us to the elephants in the room, which you can see are actually very small elephants. And they're very small elephants because there is no, in our minds, definitive evidence that deep subduction and plate tectonics contributed to what we see preserved in the Eastern Goldfields province, at least, of the Yilgarn Craton. But nonetheless, this was clearly a transition into plate tectonics that then fully developed at the end of the Archean and into the Proterozoic. So in summary, stage 1 Kambalda sequence geodynamics is dominated by vigorous plume activity, which continued into stage 2 Kalgoorlie sequence time that generated regional diapiric plutonism and volcanism. Probably also continued into stage 3A, that is Maroochal time in the late basin time period, represented by regional emergence of the landmass and the last felsic explosive volcanism. But then late basin time in Currawang, etc., represents the onset of major regional compression and shortening and the influence of crustal subcretion as a transition to plate tectonics. So thank you for listening. I'm happy to field any questions that anyone might have.